This is an activity of Seacoast, the Collaboratory for Coastal Adaptation over Space and Time. Uh, in this activity, as most of you know, different researchers from a wide range of different disciplines take turns teaching each other about the main perspectives and methods employed in their discipline in the context of coastal processes and issues. And between these live lessons and discussions and the recorded versions that we can all review at leisure, hopefully we can all start to see the coastal system through a multiplicity of different lenses and start to form some new scientific approaches that are less disciplinarily bounded. So just looking ahead for our next session in 2 weeks, we're going to have talk titled Storm Impacts and Development from Eli Lazarus and Evan Goldstein. They're going to focus on the geomorphology perspective on that set of topics. And then Catherine Anardi is going to give a talk called Storm Impacts and Development from the engineer's perspective. So really looking forward to that combination of perspectives in 2 weeks. And today we have Antonia Sebastian is going to talk about compound flood hazards in just a little bit. And we'll start with Rick Ludick with predicting water levels along the North Carolina coast. And we'll have each of these lessons will be something like 20 minutes followed by 10 or 15 minutes of discussion. And for the question procedure, you can put whatever questions come up into the chat box, either to everyone or specifically to Catherine. And Catherine will either ask you to ask your question, or if you would prefer to let her know privately, potentially she could ask it for you. With that, let me turn it over to Rick.
Well, thank you. I will share my screen at this point and lean on the crutch that we have of PowerPoint for this presentation. And thank you very much for the opportunity to join this group. What I'm talking about hopefully follows along well on what we had a couple of weeks ago that Miyuki Hino presented. And I'll try to tie into that a bit, and then also will help at least paint a picture that Tony Sebastian can follow with her talk in a little bit. I do want to say that what I'm going to talk about is obviously work that I've been heavily engaged in since coming to North Carolina 35 years ago, but it definitely reflects that of a community. And I will say one of the true community leaders that has been an inspiration in this area is Stan Riggs at ECU. And I think I might have noticed that he's on. And so we're grateful to that. And then also Casey Dietrich from NC State has been a key contributor to the technical aspects of this and continues to be a leader in this area. So again, this reflects clearly the work of a community that I'm pleased to be a part of. So the North Carolina coast, not unlike many other coasts, are areas that people tend to love. We love the beaches. In North Carolina, we love the lighthouses. In North Carolina, we have interesting flora and fauna that is attractive. We love the piers and the fishing. We love our boats, whether they're just for cruising around in or for more fishing. We love the surf. Certainly, there are many multi-generational families here on the coast that couldn't imagine working and contributing any place else. And indeed, we just love to live at the coast. And so in the future, we can really expect more people to come to the coast. And this is a slide that's inspired by Don Kirkman and the EDC, something he's been saying over and over again for at least a couple of years that I've been hearing, is just the fact that we're accommodating the ability of people to get to the North Carolina coast more and more. once back in the day, it was harder to get to it. There's a full interstate system from the Triangle to the southeast to Wilmington I-40. They're rapidly working on Interstate 42 from the Triangle to the Central Coast, the Carteret County, Morehead City area where I am at the Institute of Marine Sciences. And also a lot of work has gone into improving Highway 64, and I guess it's the future Interstate 87 that will eventually connect up to Norfolk, but bring people to the northeast part of the coast. So we love it, and more we're going to expect to have to share it with more and more people. And why do we love it? Well, it's all about the water, really. It's this place where land and water are next to each other, and so it's what kind of creates the things that we love about it the most. But the reality is that the water is really a double-edged sword, and as we learned from Miyuki a couple of weeks ago, on sunny days, it's problematic, and she told us a fair amount about what's going on in Annapolis and a bit further north. But this is the town of Beaufort here in Carteret County, and on a sunny day and the right conditions, there's water on Front Street in Beaufort and impacting the storefronts there. And in fact, Miyuki and Catherine are busy working on sensor systems that help us track how often this occurs and help us understand what exactly is driving this. But we certainly know that again, even in fair weather, water can be a problem. And then of course, particularly during storms, it can be a real big problem. And this is true again in coastal North Carolina, but it's true coast-wide, both in the United States and globally. In North Carolina, and depending on where you are, the types of storms that impact you and cause the greatest water issues might be different. In the Southeast and Gulf Coast in particular, we worry about tropical cyclones or hurricanes, but nor'easters and winter storms and extratropical storms can also create their share of hazards and challenges. So we're here for the water, but we also have to respect and figure out how to live with the water. And again, in coastal North Carolina, we're particularly vulnerable because of how close we are. A lot of eastern and coastal North Carolina, particularly in the northern half of the state, is to sea level. And so it doesn't take a lot of elevation of water level, either in an event or in a longer term context, to create, again, problems and areas that we have lived on as being really under threat, either from sunny day events or from storms. And similarly, and again, this is some of the things that again, Stan Riggs has been telling us for years, are the barrier islands that ring our coast are quite fragile, and we can't expect them to be in their current form of a largely contiguous landmass forever, and even necessarily for a long time. So, for example, Hurricane Dorian, which wasn't an especially strong storm, cut something like 60 inlets through the barrier islands, small inlets, and many of them have self-healed, but nevertheless, it's a process that's happening that will only get more substantive. And then some of the larger storms, Isabel in particular, but others as well, have cut larger inlets through the barrier islands that man has actually had to put back together again, and rebuild the roads and all of the things, the infrastructure that's out there. But that is what the future is. And so again, we in North Carolina are particularly vulnerable to the threat of water. And so it kind of begs the question here, is the North Carolina coast a safe place to be? And particularly, can we predict what the threat is from water at the coast? That's really the goal here. And hopefully a little bit better than the roll of a dice, and recognizing the fact that there's a lot of different interests that would like the answer to turn out one way or another. And so again, we want to be here, and there's money to be made here, and yet the question is really what is it like, and what is the threat like? And so this takes a couple of different forms. One is, can we predict sort of statistically what's the percentage, what's the probability that if I buy a house on the coast, it's going to be there in some number of years from now. And so statistically, we'd like to know what the threat is today. We also really want to know what it is going forward into the future, and to what extent climate change and the things that are associated with climate change are impacting what that threat is. And then we also would like to know if we're engineering some of these systems, what the implications of those are, either positive or negative. And much of the engineering is to try to mitigate the situation and build defenses of one sort or another. So can we predict what these things look like, and then statistically, and then of course, if you're here for a particular event that happens to be coming your way, can we forecast what's going to happen in this specific event? So to help you decide whether you need to evacuate, take protective actions, et cetera. So all of these are questions that help us better evaluate whether being on the North Carolina coast is actually a safe thing to do. And of course, my perspective on this is, yes, we can predict many of these things. And I have worked for a number of years, again, with a broader community, to try to build up a coastal hazards modeling system based on the ADCIRC coastal model. And it reflects meteorological forcing, it reflects tides, it reflects waves, and I'll come back to it and take it apart a little bit. But the idea here is that with an appropriate modeling system, we can start to answer some of those questions of, can we predict these things? So, so before going into it, just as sort of a bigger picture issue, coastal areas are complex, and one of the intriguing aspects of my decision to come to North Carolina 35 years ago was the complexity of the coastline, and wondering whether or not I could really, with some degree of fidelity and repeatability, if you will, predict how water moved in and around these coastal areas for a variety of reasons, coastal hazards just being one. And so North Carolina's obviously got a very complicated coastline, particularly as you consider both inside and outside the barrier islands, but so do other areas of the country and globally. A picture of the area generally around Cape Cod. And then, as you get into the Gulf, the picture on the lower right-hand corner is the Bird's Foot Delta of the Mississippi River in southern Louisiana. And that's a phenomenally complex area. And so this complexity drove or significantly impacted the choices that we made in trying to build these modeling systems to start with. And in order to run a model, a physics-based model, which is what the ADCIRC system is, you have to break the world up into a discrete grid or what we call a mesh. And that is really critical because it provides the database at essentially the corners of each of the triangles is the information or database of the physical characteristics of the area that you're modeling. And so what the water depth is, what the land cover looks like, what the friction might be like, all of the things that you need to take a set of equations and turn them into a place-based model, it is communicated into the modeling system through the grid or the mesh. And so historically, and prior to a lot of the work that we've done, meshes were Cartesian. They just look like a grid, a bunch of squares all next to each other, and the world was chunked up that way, and that's fine. Although, and so what we did with ADCIRC was say that's really not a very optimal way to build a mesh for a complex coastline. And so we developed ADCIRC using unstructured meshes, in this case triangles, and it gives you a lot of flexibility in terms of representing complexity. You can have large triangles and small triangles and zoom in, zoom out. and whatnot. And this is just kind of an example of being able to model a very large area, which is important for some of these storms because they're big storms and they may go who knows where. But yet a lot of detail in our areas like the North Carolina coast, and all the way down to being able to represent on the lower left, if you can see, beach type features, dune lines, and a variety of those things. And so this really is kind of the novelty and strength of the AdCirc model. And over the course of time that we've been working on this, there's really been a massive transition. We weren't the first group to ever consider unstructured meshes, and we built on others' technology and knowledge. But I think over the time we've been doing this, we've really brought this into the mainstream to where coastal models now may be more dominated by unstructured mesh models than structured mesh models. And that's definitely been a major change over the course of time. So, you know, I oftentimes get a question, particularly by folks that are a bit skeptical about model results, of why do we need a model to start with? If we just want to know what's going on, can't we just use measured data? And the problem with that in a coastal area and in a coastal hazards context is we just don't have that much data. This figure, they're blue dots along the coast, which are NOAA gauges. And there's about 6 of them, I think, that have been operating over some period of time for the last number of decades. Some of them much more recent than others. There's also, more recently, there's been a proliferation of the installation of gauges, and the red triangles show some that the state put in about 6 or 7 years ago, and there's the green squares are more that have been proposed. This map actually is from 2017, so I think some of these are in and functional, but the point is that even the NOAA ones have a limited duration when you're trying to create probabilities that might be 100-year duration type probabilities or even longer. And those are few and far between that we can even really begin to do that with. A lot of the data sets are incomplete. Many areas, so our longest data set is in Wilmington, and in the port of Wilmington, but the Cape Fear River has been dredged on more than one occasion, and the geometry of it's changed, so the statistics of the data that are there in Wilmington have changed. And even if we have data at each of these points, it's only at that point. And what we really want to know is how this extrapolates spatially along the entire coast, and maybe how the outer coast and the inner coast are different, and all of those things. So a purely data-driven solution just isn't practical. So we come back to the need for our model. And so again, this modeling system has, and water levels in general are predominantly driven at the coast by tides, by storm events, and we see the water level kind of rise and fall over longer time scales, but also over shorter time scales associated with waves. And so those waves interact. And so the AdCirc system attempts to capture all of these. And indeed, AdCirc can predict tides pretty well. I think just an example from Duck, North Carolina. And so data and AdCirc results. AdCirc can predict waves pretty well when you couple it with the SWAN wave model. And this is Hurricane Ophelia waves, but a lot of studies have been done, and Casey Dietrich did a lot of this work in his dissertation, and since then it's been used extensively in the system. And indeed, AdCirc can predict coastal flooding, just coastal storm surge levels pretty well as well, and when they're combined with waves and tides. And this is Hurricane Florence, and just gives you that idea of being able to do it in a spatial sense. All of the little squares are places that we have time series of data, which is great, and we can validate our model. And what you're hoping is that the little square color matches the background color, which says we got the answer about right. And way over on the right-hand side says not only can we get things right when they're kind of at their peak water level, but we can also get the time series, the progression of that water level through time. And all of that's important in terms of being able to make decisions about living along the coast. And so I will just make one quick aside and say we don't always get it all the way right. And this is in Jacksonville for Hurricane Florence, and where we got the primary peak about right from the storm surge. After that, we're clearly missing something. The black line here is data and observations, and the brown line is the model. And Tony will tell us a little bit more about that. But as a little bit of a spoiler, this is an area where it's not just about what's coming out of the ocean that matters, but it also matters about what's coming down from the sky and the precipitation and the compound flooding. So Florence was a big rainmaker as well. So let me come back to this question that I asked you a minute ago. Can we predict the threat from the coast in these different contexts? And so statistically, yeah, we can. We can use this AdCirc modeling prediction system, and we can look at historical hurricanes. We can work with colleagues to come up with a statistical representation of those. We stuff it into the AdCirc coastal modeling system, and we can come up with things like statistical curves of there's every year there's on average we'll have a 1 foot sea level event, a water level event, out to every 10 years. We'll have something that looks a little bit more like 2 to 3 foot, and out to once every 100 years, it might be up to 5 to 8 feet, etc. So we can use this modeling system to come up with statistical representations of what water level frequencies, what the water level hazard is on the coast, and we can compare them to the extent at where we have gauges. So in Beaufort, we have a gauge, and we can make some comparisons between what the model says and what the observational data says. And so that's good. And then we can also take our model and we can create surfaces out of it. And so this is the 1% annual probability water level, or also the 100-year return period. So what corresponds to this 100-year interval on this plot is just now mapped out spatially, and we can get a sense for how high the water should be if we get one of these 100-year events, and what areas will be flooded from it. So we actually can use this with some degree of confidence to map out what the present day threat is. Looking in the future with climate change, we can adjust future climate statistics for what we think the future climate will bring us. And we can also adjust sea level in the modeling system. And when we do that, we can reproduce some of our curves. And this was the same as that curve I gave you at the top a couple of slides ago. But this simply shows, here's the present day statistics. Here's what happens. The blue line is here's what happens when you add in a change in the storm statistics themselves. And then here's what happens when you add in storm statistics plus a sea level change. So instead of this being a 1% or the 100-year probability of about a meter of water towards the end of the century, with the sea level rise change and the storm statistics change, we may be looking at something that's a little closer to 3 meters of water level that we have to be dealing with. And this is specifically for the Carteret County mid-coast area. So we can make decisions, or we can understand things in the future with these models. We can also look at how modifications or mitigations will affect predictions. And so in our mesh, we can adjust our mesh either to account for dredging, to account for levees or flood walls. This is what's being done to design systems that might, this is New Orleans. This is what might someday protect the Houston-Galveston area. And we can also put in nature-based solutions. We can put in marshes, we can put in mangroves, we can do a variety of things, stuff them back into this coastal hazard modeling system to make predictions about what these would look like as well. And then just lastly, I can say that we can also run our system on a case-by-case basis when an event may be threatening our coast. And so this is just an example of what we did during Hurricane Florence for National Hurricane Center Advisory 53, put it into our system. And again, we're able to map out what water levels might look like along the coast, both spatially and as they vary over the course of time for these advisories. So with that, I will just end and say this is a lot of active work still going on in this area. We're always trying to expand the process that we can include. As I mentioned, a few of the primary ones, but there are other ones that do make a difference as we get more and more into this. And so we have ways to do that by adding processes and/or data assimilation. Again, fresh water is an issue and important. And we're also, as we think about how to convert some of these results into statistical results, we're using surrogate models and artificial intelligence and those types of techniques to try to make an impact and improve what we can do in that arena. And then just from applications perspectives, again, we continue to expand our extensions to future climate scenarios, really expanding our forecasting systems. The state of Louisiana has recently decided they're going to install our forecasting system as a state resource and a state capability, and so we're helping them build that out. And then I guess last but not least, to again connect back with a lot of others in our group, morphology change. Everything I've talked about is predicting what the water is doing, but then predicting how it impacts morphology, predicting how it impacts financial aspects on the coast, and ultimately the social societies that are there become where we're trying to head as we become more interdisciplinary in some of these capabilities. So with that, I will end.
Thank you, Rick. I've had a couple of questions come through the chat. I think I'll ask this one. It kind of piggybacks on Brad's question. So some say that the surge problem is solved. Do you agree? And what do we not know specifically about storm surge?
Well, so if you have really good meteorology, and if you have a really good representation of your, the area that you're working in, then we have a lot of confidence that we can put all of that into our models and get a fairly accurate representation of what happens in that particular instance. But then the question becomes, okay, how do you then convert that into information that's societally important and significant and impactful? And so a lot of it is how does one simply go from, how does one generalize or make better use of modeling capabilities that we have confidence in? And so I think that to me is where some of the biggest challenges are. And so there's parts of it that are certainly solved, but the big picture I think remains particularly challenging.
Okay. And then maybe Brad, do you want to ask your follow-up question here? Which I think is more broad.
Yeah, just thinking toward the future, some decades down the road, what do you think are the main limitations to being able to forecast the statistics of water levels?
Well, I think we will continue to have insufficient data to be able to use data-driven approaches. And thus, there will always be this challenge of trying to figure out what the right forcings are to put into our models, and so as to get out statistically valid answers. And particularly as we think about what may be changing over the course of our modeling timeframe. And again, morphology changes. Engineering goes on that changes the areas. Our climate is changing, and again, we're still trying to better appreciate what that looks like. So I think all of these add add a real level of challenge to what we're doing, and particularly as we look forward and try to apply these in a forward-looking manner.
Thank you.
Okay. Oh, Marty, I see something came in. Do you want to unmute yourself? I think I just gave
Sure.
people access. Okay, good.
Yeah. Yeah. Hi, Rick. Thanks for this presentation. Really interesting stuff. And I think the model itself it's really amazing to see kind of what it can do. So I want to push a little further, given kind of our broad task on Seacoast, and ask how we can think about integrating a physical model like this with some of the economic features of the landscape. So property lines, real estate data, other types of economic development. What are without being, obviously just saying, well, here it is, but like what are the challenges to doing that, and like what needs to happen in order to put these things together?
Sure. We can, under the right circumstances, give you a pretty good idea of what's going to get wet. But then the challenge is to say that, okay, so what? I mean, how does that get at the question you just asked? The engineering community, as they always do, will figure out one way or another. And so there's a lot of effort, or a lot of historical work has been done in the context of depth damage curves. If the water is 2 feet deep, here's what the economic consequences are. And so a lot of current damage estimation is done that way. I think there's a lot of progress to be made to improve on those. Just getting wet oftentimes isn't the full story. It's getting wet and what waves may be battering things down. Just wetness creates a whole set of problems, but waves on top of wetness knock things over. And so there's a lot of work that I think is being done now, which combines actually really fascinating laboratory studies with computational fluid dynamics studies at very detailed levels to say, if a wave hits a 2-story dwelling that has the following construction characteristics, will it fall over? Versus if it hits something else, what will happen to it? So there's a lot of work, I think, that's ongoing that can help us improve tremendously on our ability to say, if this hazard occurs, what the consequences of that will be. And so that's an area that's ripe for future efforts. And then, I look forward to groups like this helping me better imagine what I can tell you that is meaningful in terms of making these assessments of this sort. I think that's why there's value in efforts like this, and I think that's what's exciting about efforts like this, really.
Okay. I know that Laura has a follow-up question, but let's hold that off for a second, Laura. Cassandra, can you unmute yourself and ask your question?
Yes, I can. Hello. Thanks so much for organizing this, and thanks so much, Rick, for presenting this. My brain is more of kind of like the social impacts, so I'm excited to see kind of these other ways in thinking about water levels. So just quick question, hopefully it wasn't confusing, but I was just wondering, what are your thoughts on some of the unintended consequences for using this model to inform policy? And so I'm just thinking about communities that have been, this is communities of color, this is low-income communities, this is Black, white, Native American, Latinx, but these communities that have been like historically situated in areas that are disrupted by rising water levels. So I don't know if you can talk about any of these kind of unintended consequences that could happen.
Sure, and I probably can't do it nearly the justice it deserves. A couple of thoughts come to mind, though. One is, I always feel like better information ought to be helpful. And so one of the challenges that I think we have faced thus far is not really knowing what our threat is. And again, I don't want to potentially steal Tony's thunder here, But for example, in areas where there've been massive destruction due to water, and I'm just thinking about Hurricane Harvey, something like 60% of the damage occurred in areas that weren't delineated as flood zones. And so, I don't know, that one comes to mind, and it wasn't necessarily a coastal issue, but the point is that I think there's a lot to be gained by having a better understanding of what the threat is. So at least you have the ability to be empowered to make better decisions. Now, that's not an unintended set of consequences. That's the purpose of all of this. What ends up happening in an unintended way, and we see this we've really seen this through the National Flood Insurance Program, but also other mitigation strategies, is oftentimes we say, okay, now we know we have this hazard. We're going to design a mitigation strategy, and it might be building a flood wall around New Orleans that could fail, or it is a national flood insurance program that says, we'll give you cheap insurance so you can live there. And there's a bunch of perverse consequences that can follow from having information about what your hazard might be. And so there's a challenge at times to manage this information in a way that doesn't simply cause you to create a false sense of security and then go about your daily business. So we talk about within Seacoast levers, and so this information allows you to creates levers, if you will, and it creates the opportunity to craft policy. And what's important is to make sure that the policies you're crafting are taking you in the right direction instead of in the wrong direction, particularly as it relates to unintended consequences, which oftentimes impact minority and disadvantaged communities much more than otherwise.
All right, thanks for that question, Cassandra. I think we only have time for one more question, or one technical question, and then so Zaid, if you could unmute yourself and ask your question, and then Michael Flynn, you'll be the last question before we transition to Tony. So Zaid.
Yes, hi. Thanks for the presentation. Actually, it's very nice. But I was wondering, so we're using high frequency radar data to get wave information and to compare it on larger scale with this different spatial resolution. And I'm wondering if this one can capture the swell signature or is only for nearshore area?
Well, SWAN, the way in which we use SWAN typically is winds that are generated within the domain of interest. Oftentimes swell may propagate in from outside the domain. And in order to capture the full spectrum of energy in the wave field, you do have to propagate swell in. And so that's one of the primary shortcomings, if you will, of using a model in a restricted area like this. You need information from outside. I'm not sure that there's a technical reason why SWAN doesn't handle swell, but I'll be honest, I'm at the brink of my area of specific expertise. And so I will say, for the most part, it seems to capture most of what we're looking for, if we can at least provide the right boundary conditions for it. I will also say that AdCirc is currently being interfaced with other wave models that may or may not have better fidelity in that area.
Great, thanks for that clarification. Michael, can you be pretty quick with this question? Let's try to do 2 minutes max for this last question.
Sure thing. Hi, Dr. Ludick. First, I just wanted to say thanks for making the coastal emergency risk assessments public available. I find it particularly useful making storm preparedness decisions. And I would ask if you could expand on that bullet under applications describing the possibility of including morphology change.
Well, again, we're working and have a project that's about to come online. First off, one of our colleagues, Casey Dietrich, that I think is on the call today, has been for several years working with a morphology change model that's developed out of the Netherlands called XBeach. And so using AdCirc and coupling it to XBeach to look at morphology change, and had some good success with that. And so I think that's very encouraging. We actually have a project that's about to come online, funded through the National Ocean Partnership Program, to link that up with some of our forecasting efforts and try to run that in real time for events. So this is ongoing work with some already examples of success in that area.
Thank you very much.
All right, thanks for such awesome questions and discussion. If you want to stop sharing, Rick, let's move on to Tony.
Sure.
All right, next we have Tony Sebastian, who's an assistant professor of applied hydrology and water resources at UNC Chapel Hill.
Awesome, thank you, Brad. Can everybody see my main slide? Not
Looks
in
great.
the wrong, perfect, thank you. So thanks for the introduction, Brad. My name is Antonia Sebastian. I'm an assistant professor in the Geological Sciences Department at UNC Chapel Hill. I'm very happy to be here today, and I will mention my background is in civil and environmental engineering. So I'm kind of coming to geology from a shorter timescale perspective. My lab studies changes in coastal hazards that are driven by inland development, coastal sea level rise changes in extreme weather, and we're particularly interested in looking at how these various drivers contribute to trends in flood risk over time. A lot of our research is motivated by the observation that floodplains, as they're currently delineated, don't really capture where damages are occurring or how severe these damages might be. And so the Seacoast team asked me to talk a little bit today about compound flooding and some of my previous research around the topic of delineating flood hazards from tropical cyclone events. And I'm going to try to provide a little bit of a hydrologic or a hydrologist perspective on this topic. I found this topic to be particularly challenging because it is a very big topic right now, and it has a lot of aspects to it. So I'm hoping that I can sort of set the stage of where we are in the compound flood hazards field, but I have the feeling I'm going to leave you with more questions than you came with. So we'll see how we do on setting the perspective. But in the spirit of Disciplines 101, I've set forward 2 learning objectives. So our learning objectives for the group are to be able to identify the limitations of current riverine flood hazard mapping approaches, and to be able to describe why compound flooding is important and why it should be considered in risk analysis. And so a little bit of a roadmap to my presentation today. To set the stage, I'm going to talk about the 100-year floodplain. A lot of my previous research has focused on this topic. How is it defined from a hydrologist perspective? What does it capture and what does it not capture? And what does this mean for our ability to map and delineate where compound flood hazards may be occurring? And then I'm going to introduce or define compound flooding and talk about a couple of the key concepts and things that are going on in the flood hazards research field around this topic of compound flooding. And then finally, I'm going to provide a very short, brief example case study in Southeast Texas where we delineated compound hazards for a small coastal watershed. And then I'll sort of summarize, and this is where I think I will leave you with more questions than we started with. I'll sort of try to provide a couple of perspectives on where I think the field is and where I think we're going and where the big gaps are in the current state of research. So to start, I want to talk about the 100-year floodplain and what it is and what it is not. So the 100-year floodplain is the area that can reasonably be expected to be inundated during a flood event that has a 1% chance of being equaled or exceeded in any given year. What's important to note here is that we call it the 100-year floodplain, but it is not the area that will flood once every 100 years. In fact, It is the area that will have a 1% chance of flooding in any given year. And the reason that this distinction is important is because if you are a homeowner and you believe that you will only flood once every 100 years and you just experienced a flood, you may not take the necessary precautions to mitigate against that next flood event. In reality, if you have a 30-year mortgage, you are likely, or in the lifetime of your mortgage, you have a 26% chance of flooding. So this is this conceptual wrapping your mind, especially as the general public, around what the 100-year floodplain is in itself really difficult. The other thing that I want to note about the 100-year floodplain is that it only represents flooding that will occur from a river or a surge event. And so what we see here below, and because my presentation really focuses on river floods, what we see here below is a river system where the 100-year floodplain is the area of inundation that is flooded because the river has come out of its banks. And so this concept of the 100-year floodplain with respect to riverine flow is going to be important in the next couple of slides. I think the other thing that I want to say about floodplains while we're here is that floodplains are really they're intended as a regulatory standard. So they're there to help us determine where we should develop, how we should develop, and in some cases they drive decisions around mitigation. But because they are the only indicator of where flood hazards are in the US, they have become this de facto indicator of risk, where homeowners and emergency managers and decision makers view them as an in or out situation. So either you're in the floodplain and you're at risk, or you're out of the floodplain and you're not at risk. And this is really problematic when it comes to mitigating losses. And so these are kind of the key things I want you all to take away from the floodplain conversation. What we're seeing, let's talk a little bit of how we derive it. So there are sort of two ways that we derive the 1% riverine floodplain. One way is that we look at historical water levels in usually major river systems. We determine what the 1% exceedance probability water level would be. We put it into what we call a hydraulic model, and we get out some floodplain map. This is great when we have really long records of water levels. In most scenarios, we do not. And in most scenarios, especially for small watersheds or small tributaries where we have either short records or no gauge records, we take instead information on historical precipitation. We define what the 1% precipitation event is. We put it into a hydrologic model from which we get some flows. We take our flows, we put them into a hydraulic model from which we get some water levels, and then we take those water levels and we map the 100-year floodplain. And what I want to point out here is that inherently the assumption that we're making is that a 1% precipitation event will generate a 1% flood event. And that in itself is also a bit of a problematic step. And what we've observed over time is that lots of damages are occurring outside of floodplain boundaries. I think Rick alluded to this already for Hurricane Harvey, but in general, we see nationwide that since the advent of the NFIP, about 25% of all damages are occurring outside of the FEMA floodplain boundaries. This fraction is even higher in coastal areas. So in one watershed, and the watershed I'm actually going to talk about in this presentation, we found that 75% of losses between 1999 and 2009 occurred outside of the floodplain area. And this article got a lot of press and a lot of hits. It was on John Oliver, et cetera, and that's all fine and dandy, but I think it's important to note that in coastal areas, we're kind of seeing this as a trend across the board. We're not really capturing where the flood losses are. The other place we're not really capturing where the flood losses are is in urban areas. And there's a couple of reasons why we might not be capturing flood losses or where flood damages are actually occurring. One reason is because of non-stationarity. So if you're experiencing development upstream, or if climate is changing, so you're having higher precipitation events or if sea level rise is increasing, those changes aren't captured by the floodplain. This is because the floodplain is only mapped on average every 10 to 15 years. So if we're only mapping every 10 to 15 years and things are changing on annual or even decadal timescales, that's not necessarily captured in our mapping process. That's not to say our models are wrong, it's just to say that we don't update them regularly. And one of the reasons we don't update them regularly is because this mapping process is extremely arduous. So I mentioned previously that we take a rainfall event and we plot a given floodplain, and we're doing this on a tributary by tributary basis for the entire US. So what this ultimately means is that a variety of engineering firms are involved in mapping the floodplain, and we're doing this for thousands of different tributaries across the US. And so this updating process is not happening annually, it's happening every 10 to 15 years and kind of on an ad hoc basis when there is a need. So that's kind of the non-stationary component of this. The other component of this is that there are two types of hazards that we don't currently represent in the floodplain. At the beginning of my talk, I mentioned that the floodplain represents the area of flooding due to a river event or a coastal storm surge event. There are two other types of flooding. One is pluvial flooding or urban flooding. This is the type of flooding that occurs when you have extreme rainfall and you experience street flooding or ponding because the rainfall causes flooding before the water can reach a receiving body or stream. And so you can get pretty deep inundations in your urban areas, mostly because the water can't infiltrate or it can't run off fast enough before flooding begins. And Miyuki kind of alluded to this last week already when she was talking about rainfall and sea level rise combinations. The other reason is because our models don't capture what we're calling as compound flooding. And so here, compound flooding is the interaction between storm surge and rainfall runoff. So our current models don't represent the physical interactions between storm surge coming up from the coast or inland flood waves coming down through a river system. And I really like this picture, and Rick already mentioned that Florence is a great example of a compound flood event where we had really extreme precipitation inland and a fairly large surge event down at the coast. And there was some interaction between these two things happening in the coastal transition zone that wasn't being captured in our traditional modeling framework. And so this sort of brings us to the topic of compound flooding. So what is compound flooding, or how are we going to define compound flooding for this presentation? There's been a lot of discussion in the literature about what a compound event is and how we define it. And we think about compound events across many different types of hazards. So this definition can vary considerably. So for the purpose of this presentation, I want to constrain our definition of compound flood events to the co-occurrence of two flood mechanisms happening in space and in time when their co-occurrence results in more extreme flooding than either in isolation. So I'm going to point out a couple of things about this definition before we move on. First of all, it requires that these two events are occurring together in space and time. So I'm not considering events that might occur 1 week apart. I'm not considering, a rainfall event followed by another rainfall event or a rainfall event followed by a tropical cyclone. We're truly thinking about things that are pretty much overlapping in space and time. The second part of this is that the combination of these two events occurring are more extreme than either in isolation. So here, this is this physical interaction that's occurring between these two mechanisms. So thinking about storm surge and rainfall runoff coming together in the coastal zone and interacting to create more extreme flooding than if you had one or the other. The key about compound floods, or what makes them so complicated, is that we think about them very differently from a modeling perspective. Whereas when I talked about the fluvial flood event, where we're picking either a water level in a river or we're picking from the historical rainfall events and we're defining a single distribution that describes that exceedance probability, when it comes to compound events, we start thinking about two or more variables. And here we need bivariate distributions, which means that we have a distribution that describes every variable in our model, but we also have distributions that describe the relationships between those variables. And for any of you who have looked at the compound flooding literature, there is this term called copulas that is very, very prominent, or it has become a method for estimating this bivariate distribution that a lot of people like. And the only thing I want to say about that here, because we're trying to keep it simple, is that one of the advantages of copulas for representing this bivariate distribution is that they're great for representing environmental data where there's kind of a lot of messiness to it. So they don't require that these two distributions follow the same distribution. They can have mixed distributions, and they can represent sort of this environmentally messy data as sort of a point cloud. So just to keep things simple, I wanted to bring that up. So what have we been doing in this compound event analysis field? So one thing that a lot of researchers have been focused on is trying to identify where there might be hotspots of co-occurring annual maxima or co-occurring extreme events, particularly for large river systems. We've seen this in the US, we've seen a couple of papers come out globally, and these either use historical water levels or modeled water levels to try to get at where do we think these things will occur in the world. And so this is a paper by a former student of mine that she worked on recently during her PhD, looking at co-occurring annual maxima for large river systems around the world using modeled data. And while this highlights some areas, so the darker points highlight some areas where these co-occurring annual maxima are very likely to occur, what it doesn't really highlight for us is the hazard associated with these co-occurring events, or what might be happening in some of the smaller watersheds that aren't associated with major river systems. And so that kind of brings us to this case study. So we have this question, this looming question of how do we represent the flood hazards associated with compound events, especially in our small coastal systems, where these co-occurring events might drive really extreme impacts for the populations that are living there. A lot of my PhD work, so I did my undergraduate and my graduate degree at Rice University. I lived in Houston for many years, experienced a lot of really massive storm events. And my research really looked at this Houston-Galveston Bay region. So Galveston Bay is the 7th largest estuary in the US. I've kind of picked out 4 key areas here. It's characterized by barrier islands, both unprotected and protected. So we have sort of the barrier islands. This is Bolivar Island and the city of Galveston, which is located behind a seawall. There's the Houston Ship Channel, which is the 2nd largest petroleum processing facility in the US and shipping port in the US. And then there's also this West Shore area. And this West Shore area is home to NASA and a couple of other really significant industries. And it's characterized as extremely populated. So the whole region has about 6 million people living in it. And this West Shore area has a large fraction of that population. And this West Shore area is subject to extreme storm surge that occurs because hurricanes are rotating. I don't know if everybody can see my mouse, but hurricanes are rotating counterclockwise over this bay system. So what we see is as they approach the coast, they push water into the bay system and their winds push water up into that West Shore area. But it's also very vulnerable to extreme precipitation. So the watersheds on this West Shore side are quite small. So a heavy precipitation event can drive a lot of pluvial flooding, so flooding just occurring because of the heavy precipitation, but also a lot of riverine flooding with a very small time lag. So the time difference between when the rainfall falls and when we see river flooding in these coastal watershed systems is quite fast, which means that if you have a hurricane event and you're experiencing storm surge and rainfall runoff, they're very likely to coincide and drive extreme impacts in this coastal zone. So I kind of want to point out how complex the system is. So I sort of just described this to you conceptually, but I really like this framework that was proposed by Michelle Bensi in 2020. So she looks at compound events or multi-mechanism events as being able to be divided into flood forcing phenomena, flood mechanisms, and flood severity metrics, where this whole thing is the hazard process that's occurring. And so in our case, in our system that we're looking at, we have tropical cyclone events and natural astronomic processes. that drive a variety of different flood mechanisms. And here we can see that a tropical cyclone is going to drive precipitation, storm surge, and waves. And this storm surge and precipitation together also can drive riverine flooding. And the astronomic process just drives tide. And when we have all these things co-occurring in the watershed, together they combine to create more extreme flood depths and extents. And I'm really interested in how we can quantify these flood depths and extents. But in order to do so, we have to understand both the processes that drive the mechanisms and how the mechanisms come together to create the extent. And our primary challenge in this area, and this is work that I did during my PhD, is trying to get at the statistics of the events that we might see in this area. So we have very limited, we have great long historical records of water levels down at the coast, but we have really limited and short records inside of Galveston Bay. So both spatially and temporally, we're really limited in the data that we have in Galveston Bay. But we have a pretty good understanding that storm surge is a problem here. On the other hand, I will mention we have great rainfall data. We have lots of gauges, lots of long records of rainfall data. And so in trying to figure out how we were going to define joint boundary conditions for this coastal watershed, we needed to fill our records somehow using the limited data that we did have. And the way that we ended up deciding to do this, or maybe I'll back up just a step and say, when we looked at our historical record, even down at the coast, we've only experienced about 30 or 32 at the time of this study tropical cyclones that created significant water levels in the bay, where I define significant water levels as like greater than 2 feet. And so what we wanted to do was expand our record of tropical cyclone events for all of the historical record that we had available to us. And the way that we did this is we collected all of the storms that had ever made landfall in the Gulf of Mexico. And we used them to generate a data set of tropical cyclone characteristics, as well as the precipitation and the storm surge that was created in our bay system. And the reason that we felt really confident in doing this is because we also used a variable of landfall location. So even if we had a storm way over in Florida, because we're using landfall location to define its relationship to Galveston Bay, if it created no precipitation and no storm surge, it wasn't a big deal, but it still allowed us to incorporate those other records into our database. And as I mentioned way earlier, copulas are kind of a popular method in the compound world right now. So one of the things we did in order to relate all these characteristics of our hurricane is we built a non-parametric Bayesian network. And just really simply, a Bayesian network allows us to relate every variable in our network based on those joint probability distributions between the characteristics. So for example, as I just mentioned, the distance to landfall versus the surge that we observed in the bay, that has a probability associated with it, or space, a probability space associated with it. And we could define that probability space within our network and use it to help build our network. And this is the network structure we ended up with. And what I want to point out here is that these darker colors are all of our hurricane parameters, and these lighter colors are our surge and our precipitation. And the whole goal of this study was to take the historical tropical cyclone records, all 600 of them, and use them to generate estimates of surge and precipitation based on their characteristics. We also had to do a little bit of translation to get our coastal water levels up to where our watershed was. And as a result of the Bayesian network analysis, we were able to sample the events, the historical events in our record 100,000 times and develop this joint probability space from which we could derive combinations of cumulative precipitation and peak surge. And here you can see these red dots are real events in the record, and these lines sort of represent the joint probability distributions of surge and cumulative precipitation. And I don't want to focus too much on that, but what I want to bring it back to is this issue of needing to model flood hazards. And so early in the presentation, I talked about taking a single boundary condition, whether that was water levels or precipitation, and running them through our modeling framework to generate a floodplain map. What we've now done is we are able to take all of our tropical cyclone events that we've ever seen in the record, relate their characteristics to precipitation and storm surge and a time varying random tide, plug them into a hydrodynamic model and estimate the flood hazard associated with the compound events that we've seen in our record. And so this is a huge step over where we've come from. So this deterministic approach of taking single boundary conditions and estimating river or coastal surge to moving towards compound events. So that's just my little example. And here I want to leave you with my concluding remarks. I think I had a really limited time to say a lot about compound flooding, but there's so much more that could be said, and it was hard to pick off a few things to talk about. So I just want to leave you with this. There's a growing recognition that flood hazards are occurring outside of delineated flood hazards areas. We have a pretty good understanding of what might be some of the causes of this, but it deserves a lot more research to understand relative causes, as well as how those different causes combined might be affecting changes in the flood hazard profile. Compound research to date has sort of focused on two key topics. One is this issue of identifying hotspots where concurrent hazards are likely to occur. So for example, rainfall and coastal water levels, high river flows and storm surge. And the second focus of research has sort of been on this modeling the extent of flooding that might be caused by these combined events, or trying to identify the transition zone. The primary limitations in this modeling topic are related to the lack of historical data on co-occurring extremes, particularly in small watershed areas. So we have great gauge data on river systems, or we have pretty good coastal water level records that go pretty far back in time, but they tend to be spatially disparate, and we don't have great information, particularly in the small coastal watersheds that are often really heavily populated. A second problem that we have is a lack of resolution in large scale or global models. Rick sort of hinted at this in his presentation, but one of the things we're working on is trying to refine the AdCIRC grid, as well as some of our hydrologic and hydraulic models, to better capture sort of topobathymetry of these coastal areas, which might be really important in trying to capture compound events. And sort of the third area, which I just felt like we didn't have time to talk about today, is model coupling. So right now, in our ability to capture compound events, or when we try to capture compound events, we tend to be coupling multiple models into cascades. So big coastal ocean water level models with inland hydrology models. And this coupling process is very difficult and is an area of a lot of research. Then I want to say, yes.
Tony, maybe we can leave it there so we can have about 5 or 6 minutes for questions. Okay.
Perfect. Yeah, I'll stop.
Great. Okay, thank you, Tony. A wonderful talk. I'm going to give a little bit of time for questions. Maybe I shouldn't have cut you off, but I realized that I've never asked you, as somebody that cares about sand and river discharge, do compound events have an effect on sediment delivery to the coast?
I don't know if I have an answer to that question, but I would imagine that they would. So the modeling that I do, I'm not usually incorporating sediment transport into my models, but I would imagine that this dynamics that's happening in the coastal zone, where you have a wave moving upstream and a wave moving downstream and combining somewhere along the way, probably does significantly drive how those transport processes are occurring. But I don't know if I have an answer for you of like how and when.
I definitely can't model that problem, but maybe somebody here could do that.
Maybe we need better models first.
All right. Any other questions for Tony? Oh, Brad, can you unmute yourself?
Yeah, it's kind of the same question as I asked Rick, but if you're thinking about trying to forecast the statistics for some decades in the future, clearly not knowing the forcing conditions and meteorological statistics is a limitation, but do you think that's a bigger limitation compared to the characteristics of the landscape that are more in control of people's decisions over the next, that let's say a few decades into the future, the decisions that are made between now and then affect the flooding through the landscape?
Yeah, I actually think that that is a very interesting question because people's decisions about where they develop and how they develop is going to be driven by their risk perception in many instances. So there's kind of a feedback loop that's not being considered in the future modeling of land use projections right now. So most of the future projections we've done are sort of deterministic, as like, we're going to keep developing the way that we're developing, plus or minus some regulation, right? So I do think that there is considerable uncertainty in our ability to project that future land use. I think some of the interesting results that I've had in some of my previous research is also that the combination of climate changes or meteorologic changes and land use changes tends to be more extreme than either of those in isolation. So there's sort of a, sorry, I'm blanking on the words, a compounding effect, to not be able to use a better term right now, a compounding effect of land use change and climate change coming together to drive more extreme flooding as well. So I definitely think a lot of work has been put into the meteorological forcing, but I think in our future projections of land use, it's still somewhat deterministic.
Thank you.
I am calling on Marty. Marty has a question.
Thanks. That was a great presentation. I really like the figures with the joint, the Bayesian network and the joint probability with the actual events overlaid. That really just jumped out as being provocative, which made me think, how much do people in real estate markets, like how much do they understand the work that's coming out of your lab? How quickly might this start to have feedbacks on people's understanding of risk? And I know that that's not exactly your area, but to me, it's just a fascinating question. Like, we're getting what I think is sort of fundamentally different information about risk by modeling compound events. And that should fundamentally alter how that's capitalized into real estate. So I'm just wondering your thoughts on that, and what is the timing? Like, how new is this, and when will we have a better understanding like this of multiple geographies and things like that?
That is a very interesting question. The speed with which the regulatory models are catching up to what we're doing in the research or the lab space is, we're seeing it. There are more and more conversations about how do we get this into practice right now, that are happening right now than compared to 5 or 10 years ago. So good question on like how fast, but I think the question about real estate and capturing this or portraying information to homeowners in different ways or making information more public is a really interesting one, because as I mentioned earlier in my presentation, we have this 100-year floodplain, which is like the de facto indicator of risk, but it doesn't actually provide us any information about what the risk to my property might be in terms of dollars, like economic damage over a given time period, or what the depth of water is. Sometimes that information is available, but not always. And so though there's some other research that I'm involved with peripherally, but those questions about how do you provide the information to homeowners in ways that don't have negative effects, that might promote proactive decision making, but you also don't want to like scare people. Those are really interesting questions. How do we take our floodplain maps and provide that information to individuals in a more realistic manner with that could help promote change?
Okay, we are out of time. But Jana had such a great question. Maybe Jana, you can stick around and ask your question to Tony, but we're out of time. There's another one. Such great questions. Thanks for coming, everybody. We really appreciate it. Thank you so much to Tony and Rick.
Yeah.
If you can join Seacoast, there's a survey on our website. We're trying to create a network. We're trying to do this through maintaining a directory. You can also follow our activities on Facebook, on Twitter, and checking our website. So Laura posted all of those links in the chat. So thank you, everyone, and have a great day.
Thank
And
you.
come back on our last session and hopefully we can revisit some of these questions we didn't get to as well during conversation. And thank you, Catherine.
I need to stop recording.